Hey everyone, welcome back to another video on the channel. Today we're going to be doing something probably the most fun thing we've done so far. So to start off, what do you see in front of you? Well, here you may or may not have seen this, but if you're into electronics and all that kind of stuff, and you've maybe if you've used a hammer or just broken down a piece of electronic device, you might have seen something like this. This is a circuit board. It's inside every electronic device, and it has various transmitters and other things that power the device. Now, a subversion of this, a smaller version, would be like an AC circuit, which is the thing down here. Now, in the left, you can see an example where an AC circuit is powering up a light bulb. And on the right is a graph of the frequencies and the electricity frequency graph that's being plotted. So in all the previous videos, we did some complex numbers. We started doing some complex numbers things. And this video is the real deal. How can you use whatever that happened into AC circuits? Now you may be like, how does complex numbers even go into AC circuits? This looks so weird. I don't remember anything related to AC circuits that are even close to complex numbers. But let's take a look. So we're going to be trying to solve for the impedance in this circuit. Now, as you can see, the various things here are, for example, the first thing is the AC here, which means AC circuit. Then the R here stands for reactance. So R stands for reactance. XC, or R is resistance, my bad. R is resistance. XC and XL are the two different types of reactances. Now, you've reactance as a separate thing, which is usually what an AC circuit measures, and XC is the capacitive reactance. Capacitive reactance, and XL is the inductive reactance. Now, this is not a complete discussion on AC circuits. It's just the applications of complex numbers to it. So if you don't know what these terms mean, you should just do a little bit of reading and then see how complex numbers can be applied. Honestly, to see the application, you don't need to know what these terms are, but if you want to get into AC circuits more, you do need to know them. So the first thing what we're going to do is we're going to make, what's it called? What do you think we do with complex numbers? That's right, we make a graph. So I'm not going to include the negative axes on this one, I'm not going to include negative x on this, just positive, I'm not going to include the negative real axis, just the positive real axis for this one. Let me make it a little bigger. Okay. That's the imaginary axis, and to denote that, I'm going to put the imaginary symbol. And this right here is the real axis. And to denote that, I'm going to put the real symbol. All right. Now, use everything today to find the impedance. Oh, by the way, and tell you we're going to solve for Z, which is the impedance. This is what we're going to be solving for in this circuit. Everything we do to solve for this is going to be happening in this graph here. And the first thing you're going to do is graph the capacitive reactance and the inductive reactance. The capacitive reactance is always on the negative imaginary axis. So in this case, we see that the capacitive reactance is 40 ohms. So we're going to graph 40 ohms on the negative imaginary axis, and the inductive reactance is 80 ohms, so that's on the positive imaginary axis. So if we go down and we say 40 ohms is about here, but let me make it a little higher up. That's 40 ohms for 40 ohms. Negative 40 on the actual graph but for AC circuits, we're just going to use 40. And this is the capacitive reactance. Then the inductive reactance is on the positive imaginary axis. And in this case, we remember the inductive reactance is 80 ohms, so we're going to graph it up here. Let's say that is 80 ohms, and that's the inductive reactance, XL. So we've got the two graphed on the imaginary axis. Now, what is the real axis for? Well, the real axis, this is easy enough to understand, is for the resistance. You see, the R and R for resistance. So in this case, we see that the resistance right now is 30. And we're going to go ahead and put 30, which will be right there, and that's the resistance R. Now, if you remember complex numbers, what we need to do, the first thing we need to do is find XL minus XC to find the total reactance of the circuit. We have two types of reactance, capacitive and inductive, so to find the total, we simply add them up. How do you add them up? Well, you see, XL, it's not XL plus XC. Remember, XC is in the negative y-axis. It's XL minus XC. And in this case, XL is 80 and XC is 40. So 80 minus 40, which gives us 40 ohms of total reactance. This is the total reactance of this AC circuit. So now we're going to go ahead and graph this 40, which is going to be right up here. Now, this is the total X reactance. Then, to solve for the impedance, the thing about the impedance, it is always the formula for the impedance. Z is equal to resistance plus I times your reactance, X. This is the formula for impedance. Let me write down to make it clear that we're solving for the impedance in this circuit. Now, as you remember, in this case, I is not a variable. I squared is -1. This is the I we're using. Now you can see how the complex numbers really comes into play here. So to find Z, all we're going to do is plug in the numbers. We know the resistance in the circuit is 30, as we've graphed it. So all we're going to do is 30 plus what is X, the total reactance. We just found that. It's 40. So it's 30 plus 40I. And guess where that complex number is? That's right. It's exactly somewhere there. I'm going to go 30 up. I'm going to go 40 up and 30 to the right. And that is Z, which is equal to 30 plus 40I. See, now you can get the idea of the complex numbers graphing on the graphing. Remember, we did this graphing complex numbers on the complex plane. This is exact same, nothing new, just we were using fancy terms and in AC circuits. Now, this is Z, but to actually make use of anything we do in Z, we have to find the magnitude of Z. So to really make use of the impedance, we got to find this value, the magnitude of Z. Now, this is where another thing from the previous video comes in. Do you remember the formula for the magnitude of a complex number? That would be Z is equal to the square root of A squared plus B squared. Honestly, you don't need to memorize this. You know the Pythagorean theorem, then you know how to do this. Now, in this case, 30 is A, and 40 is b. So this is equal to the square root of 30 squared plus 40 squared. And if you evaluate that, you'll find that you get 50. Now, again, if you didn't see this beforehand, you didn't really have to go through this process. You could already know, you could start drawing a triangle. You could start drawing a triangle like this, and you'd see that this is actually a 3, 4, 5 right triangle, and the hypotenuse is 5, but each side is being scaled by 10, so you can just get this length as 50. And therefore, this is the final part of the AC circuit solving, and that is Z, which is the impedance which is 50. And that's how you solve for impedance in an AC circuit. Now, again, as usual, we did it with numbers, and you know the drill. All we're going to do is generalize it. Let's make a copy of that graph again. I'm going to draw a line here. And now we're going to draw a new graph, but this time I'm going to make it smaller. So, because we already knew from the big graph how it looks, right? This is the real axis, and this is the imaginary axis. Now let's say we have a resistance R plotted. We have an inductive reactance XL here, and we have a capacitive reactance XC here. To find the total reactance, we do the same thing as before, which is XL minus XC. Only this time we're just going to leave it here because we don't have any numbers to plug in. So after we're done doing all that, we'll find that XL minus XC is somewhere over here. Then to find the impedance, the coordinates of the impedance would be Z is equal to, remember the same thing, total reactance, which is X plus I into R. We found the value for X, and that is going to be XL minus XC plus I plus RI, or IR. I just wrote, generally you'd write IR because that's just the style of writing it, but I wrote RI this time to get into the BI format instead of IB. And finally, to solve for the magnitude of Z, that's equal to the square root of the reactance squared plus the resistance squared, which is equal to, the last step is to plug in the reactance, which is XL minus XC squared plus R squared. And that is your formula. There you have it. This is the formula for impedance. This is the most important takeaway from today's video, that the formula for impedance, given the capacitive reactance, inductive reactance, and the resistance, is this right here. Now, just to make sure the terms, you don't forget the terms, this is the inductive, and I'm not going to actually write the full reactance. I'm just going to leave it at this. XC is the capacitive reactance, and R is the resistance. And that is the beauty of complex numbers. And you don't just have to apply complex numbers to AC circuits. It's the most applicable in AC circuits because the adding and subtracting and magnitude, all the computations make it so easy to calculate. But you can use it in normal Euclidean geometry just by, or in fact, analytical geometry if you want to, because instead, if you just convert everything from a normal Cartesian plane to a complex plane, it makes it so much easier to work with. and you can compute it much better because you adding numbers on the complex plane works much differently. You can't actually add numbers on the Cartesian plane, whereas you can add numbers on the complex plane. So that was the full major takeaway from this video. Thank you so much for watching. Hope you enjoyed this video, and if you're interested in AC circuits, make sure you know your complex numbers or it'll come haunt you someday. See you next time.